Welcome to AI Paper Slop. We are tearing into a really monumental paper today titled Improving the Matrix Multiplication Exponent with Modern Optimization and AlphaEvolve.
Yeah, this one is massive.
It really is. It's from a collaboration between researchers at Google DeepMind, Carnegie Mellon, Columbia, and MIT. And if you're looking for the core insight right now, just right up front, here it is. The authors established a new state-of-the-art upper bound on the matrix multiplication exponent, which is a value known as omega.
Right, the absolute theoretical speed limit.
Exactly. They brought that bound down from 2.371339 to 2.371177. And they achieved this by basically taking a purely theoretical computer science problem and just treating it like a machine learning engineering challenge.
Which is such a wild pivot.
It is. They used gradient descent in JAX. They replaced all these rigid, hard constraints with the Sinkhorn Op algorithm, and they scaled the recursion level of the combination loss analysis from 3 up to 4.
Which totally exploded the parameter count, right? From about 25,000 to like 7 million.
Yeah, 7 million. And ultimately, they used an AI agent, AlphaEvolve, to refine the optimization algorithm itself.
It's a phenomenal collision of two totally distinct cultures. You know, you have theoretical computer science, which typically relies on these incredibly rigid, manual, exact mathematical proofs.
Yeah, very pen and paper math.
Exactly. And then you have the messy, approximate, gradient-driven world of modern machine learning. And seeing them integrated this seamlessly is just rare. But to understand why this matters to you, the technical practitioner, we really have to ground this in what omega actually represents.
Yeah.
And like why an entire subfield of mathematics is dedicated to shaving just microscopic fractions off its value.
Well, matrix multiplication is the foundational operation underpinning, literally everything we do in deep learning, computer graphics, scientific simulation. It's the core of the transformer architecture you use every single day.
Absolutely. It's everywhere.
So if you multiply two Mon times matrices together using the standard method we all learn in school, it takes one operations. You multiply every row by every column. But back in 1969, Volker Strassen published a paper proving you could do it in slightly fewer operations.
Right, by combining submatrices in this really clever way.
Yeah, he proved you could do it in a low nega, where omega was strictly less than 2.81, and that single realization basically kicked off a 40-year race to find the true bottom limit of omega.
And over the past few decades, virtually all the improvements to that bound have relied on this massive mathematical framework known as the laser method.
Which sounds incredibly cool, honestly.
It does sound cool. And the current state-of-the-art relies on a very highly specific refinement of that method called combination loss analysis. This is what the previous benchmark, the one published by Ullman and colleagues in 2025, used to get the bound down to that 2.371339 number.
Okay, so that was the baseline going into this new paper.
Right. But combination loss analysis comes with this brutal built-in bottleneck.
Yeah.
It revolves around a trade-off parameter called the maximum recursion level, which they denote as dollars.
And the dollar parameter basically dictates how deeply you recursively decompose a specific starting tensor, right? The Coppersmith-Winograd tensor.
Exactly. The deeper you go, the better the theoretical bound on omega you can prove.
But let's play devil's advocate for a second here. If you're an ML engineer working at a major lab today, you might look at a trade-off parameter like $1 and think, well, we have clusters with tens of thousands of GPUs now.
Just turn it up.
Yeah. Let's just turn a level up to 10 and brute force the computation. You might imagine it like rendering an incredibly complex 3D fractal or something, right? You just throw more spatial compute at it until the image finally resolves.
Yeah, the fractal analogy is tempting, but it really masks the true nature of the scaling we're dealing with here. We aren't dealing with a spatial rendering problem. We are dealing with a combinatorial explosion.
Meaning it gets very big, very fast?
Yeah, doubly exponentially fast. The complexity of the optimization problem grows doubly exponentially with the loss. When the Ullman paper hit their 2025 benchmark with $3 is 3.3, the optimization space contained about 25,000 parameters.
Which doesn't sound that huge by today's standards.
No, it doesn't. They used a sequential quadratic programming algorithm, SQP, running through a software package called SNOPT.
And SQP algorithms are actually fantastic for that scale because they calculate second-order derivatives, right?
Right.
They look at the curvature of the optimization space, usually by approximating the Hessian matrix, to find the absolute optimal step to take.
But consider what happens when you attempt to move from $3.3 to $4. The parameter count does not just double or even triple. It rockets from 25,000 to roughly 7 million.
Oh, wow. So 7 million parameters for a second-order solver.
Exactly. If you try to run an SQP solver on 7 million parameters, it needs to approximate the 7 million by 7 million Hessian matrix. The memory overhead alone makes it physically impossible.
Yeah.
Traditional solvers just choke.
So the entire field essentially got physically stuck at load Oliver's equals 3T3 bill because the traditional mathematical tools hit a hard computational wall.
That's exactly it.
So the DeepMind, CMU, Columbia, and MIT researchers realized that if they really wanted to break through to low Ollers or 4 Poitras, they had to abandon the old solvers entirely.
They needed to reformulate the math from the ground up so they could use first-order machine learning optimizers.
Like Atom.
Right, like Atom,
Yeah.
which only looks at the gradient and can easily handle millions of parameters.
But to use gradient descent, your entire problem space must be differentiable. Like it has to be a smooth landscape. And this theoretical math problem is, well, the exact opposite of smooth.
Yeah, the structure of combinational loss analysis is this massive rooted tree. The root represents the original Coppersmith-Winograd tensor.
Okay.
And as you move down the branches, you are recursively decomposing that tensor into smaller and smaller tiled nodes. Each node in this tree has specific characteristics. It has a level representing its depth. It has a shape, which is defined by 3 non-negative integers.
Like X, Y, and Z coordinates.
Yeah, coordinates that must sum exactly to 2 Lollers, where Lollers is the current level. And finally, it has a region, which is just an index from 1 to 6, representing a permutation of those coordinates.
And tied to all these nodes are these really complex probability distributions. You have distributions over the regions, distributions over the shapes, and specialized distributions for nodes where the shape coordinates contain zeros.
Right. And at a traditional math solver, you enforce these probabilities as hard constraints. You literally tell the solver, these numbers must never be negative, and they must sum exactly to 1.
But gradient descent doesn't understand hard boundaries at all. It needs a continuous slope to roll down. If it hits a hard mathematical wall, the gradients become undefined, and your optimizer just crashes.
So they bypass this by parameterizing the distributions using unbounded logits.
Oh, nice.
Yeah. Instead of trying to optimize the final probabilities directly and constantly checking, like if they sum to 1, they set up the network to optimize raw, unconstrained real numbers. And then they just pass those raw numbers through a softmax function.
Because softmax naturally squashes any set of real numbers into a valid probability distribution that perfectly sums to 1.
Exactly. It effortlessly transforms a rigidly constrained mathematical box into an infinite, completely differentiable landscape. The ML optimizer can wander anywhere it wants in the logit space, and the softmax operation guarantees the underlying math always remains valid.
That is so elegant. But dealing with basic probabilities was kind of the easy part of this paper. The real nightmare here is handling the maximum entropy constraints, right?
Yeah, that was the hardest part by far. Calculating the retained exponent of this recursive tree involves finding a specific probability distribution that has the maximum possible entropy.
Okay, sounds reasonable.
But there is a massive catch. This max entropy distribution must perfectly match the marginals of a given input distribution.
Let's visualize what matching a marginal actually means for the listener, because it can get a bit abstract. Imagine a simple grid of probabilities. The marginals are just the totals at the end of each row and at the bottom of each column.
Right, the row and column sums.
So the problem demands that you find the most uniform high entropy values for the inside of the grid, but those row and column totals must perfectly match a strict set of target numbers. So if you're building a neural network in JAX, how do you enforce a strict equality constraint on marginals while maximizing entropy and somehow keep the whole process smooth enough to backpropagate through?
Well, the old SQP method just threw the maximum entropy distributions and their associated Lagrange multipliers into the pool of free parameters and just tried to optimize them all at once.
Which sounds awful.
For 7 million parameters, it creates a total non-convex nightmare. So the authors looked outside of traditional complexity theory and pulled a technique straight out of optimal transport. They used the Sinkhorn algorithm.
Right, and optimal transport is usually applied to machine learning problems involving like Wasserstein distances or Earth mover's distance. It's basically a way of calculating the cost to reshape one probability distribution into another.
Exactly. And Sinkhorn is an iterative algorithm. It takes a matrix and alternately scales its rows and columns back and forth.
Just bouncing back and forth.
Yeah, just back and forth until the marginals converge perfectly on the target values. By embedding the Sinkhorn algorithm directly inside the optimization loop, the authors found a stable, theoretically sound way to generate those maximum entropy distributions on the fly.
But wait, embedding an iterative algorithm inside a neural network introduces a massive engineering hurdle. To optimize the overall tree, you have to backpropagate the error signal all the way from the final output back through the tree and through every single step of that iterative Sinkhorn algorithm.
Which is terrifying.
Computationally.
Right. If Sinkhorn takes 1,000 steps to converge, you're unrolling a 1,000-step computational graph for every single node in the tree. The gradients will either explode into infinity, vanish to zero, or your GPU memory will just overflow instantly.
And the authors fully anticipated that memory explosion. So rather than backpropagating through the iterative loop, they utilized implicit differentiation.
The implicit function theorem is just a beautiful piece of calculus. It allows you to look at the final converged output of the Sinkhorn algorithm and calculate the exact gradient directly from that final state.
So you don't even need to store or care about the 1,000 steps it took to get there.
Not at all. It gives you pristine gradients while completely bypassing the memory overhead of unrolling the loop.
That is brilliant. So on a whiteboard, we now have a mathematically sound, fully differentiable formulation. But translating whiteboard math into a high-performance JAX implementation on a GPU cluster is a completely different battle.
It really is.
Because the tree structure we just described is intensely jagged and non-uniform. A node with a specific shape might have dozens of children, while a zero-shaped node has absolutely none.
And GPUs are fundamentally designed around SIMD architecture.
Single instruction, multiple data.
Exactly. They process data in groups called warps. A GPU wants a massive, dense, uniform block of data so that all 32 threads in a warp can execute the exact same instruction at the exact same time.
Right. They want predictability.
Yes. If one thread is working on a node with 5 children and another thread in the same warp is working on a node with 0 children, the threads diverge. The GPU has to serialize the work, and your parallel processing speed essentially drops to 0.
So how did the previous 2025 algorithm handle it?
They handled the tree using a loop-based message passing system on CPUs. The parent node sends a message to the child computes and sends a message back. It is inherently sequential.
You cannot force a highly irregular, jagged tree structure into the perfectly square execution model of a GPU.
Unless, of course, you fake it.
Right. Unless you fake it using phantom nodes.
Yeah, the phantom node technique is just a brilliant piece of engineering. The researchers systematically padded the sparse areas of the tree structure. Wherever the tree was uneven, they inserted fake nodes to just square off the jagged edges.
So they transformed a chaotic tree into a perfect, uniform hypercube of data.
Precisely.
Think of it like building a massive, perfectly rectangular scaffolding around this asymmetrical, wildly shaped building. The construction workers, which are the GPU threads in this analogy, now have perfectly straight, continuous lines to walk on. They never have to stop and figure out where the next step is.
But they do have to ensure the fake nodes don't corrupt the actual math. So they aggressively masked out the phantom nodes during the actual computation steps.
Yeah.
A trade-off is that adding all this scaffolding increased the number of optimizable parameters by a factor of 3. They intentionally made the mathematical problem 3 times larger.
Which sounds completely counterintuitive until you see the payoff. By regularizing the graph, they were able to cluster the nodes into specialized stages and represent the entire optimization problem as massive, multidimensional tensors.
Huge tensors.
Yeah, we are talking about tensors with up to 10 axes, and JAX is uniquely built to take a 10-axis tensor and just seamlessly distribute it across parallel hardware accelerators.
Exactly. They took an algorithm that was choked by sequential CPU loops and turned it into an uncompromised tensor crunching machine.
It is amazing.
And with the JX engine running at full speed on that little all-force forward parameter space, the gradient descent approach alone secured a massive improvement. So the previous state-of-the-art bound from 2025 was 2.37133 line.
Right.
The pure gradient descent formulation improved that bound by about 97 pace 10 to 4 all. In the slow, grueling history of the laser method, that is a huge lead forward.
But they didn't stop there. They wanted to push the architecture to its absolute physical limit, so they introduced an AI coding agent into the loop.
Yeah, they brought in AlphaEvolve,
which is an agent designed specifically for scientific and algorithmic discovery. And they didn't just ask the agent to tune learning rates or adjust hyperparameters. They tasked AlphaEvolve with generating modifications to the optimization code itself.
The AI was literally rewriting the JX code that optimized the theoretical math problem.
That is wild.
One of the most effective techniques AlphaEvolve discovered during this process was a feature called evolving constructions. When an evolutionary algorithm generates a new, mutated version of a program, it usually starts the optimization process from scratch to evaluate how good the new code is.
Right, it resets.
AlphaEvolve modified the system so that each new generation inherited the best solution point found by its parent algorithm.
So it's effectively hot starting the search.
Yes, exactly.
The new mutated algorithm doesn't have to wander through the early, easy parts of the parameter space. It picks up the baton exactly where the previous generation left off, but it drives the gradient descent using a potentially more efficient AI-generated search logic.
And they ran AlphaEvolve on a single GPU for roughly 5 hours. In that short window, the mutated code bumped the improvement up from 97 times 10 to the cells to roughly $1.62 times 10 to 4 over the 2025 baseline.
Wow.
That final push is what secured the new world record upper bound of omega, less than 2.371177.
Now, any technical practitioner listening right now is likely slamming on the brakes. You are probably asking a very obvious, glaring question. How can a 32-bit floating-point GPU training run ever constitute a rigorous mathematical proof?
It's a very fair question.
Because GPUs use float-32 arithmetic, which is famously imprecise. If a GPU rounds a decimal incorrectly at, like, the 8th decimal place, your inequality constraint fails and your mathematical theorem is completely invalid. You cannot publish a theoretical computer science proof based on approximate float-32 gradients.
You can't, which is why the authors build a rigorous certification pipeline to bridge the gap between those machine learning approximations and mathematical certainty.
Okay, how did they do that?
They took the final floating point solution generated by the GPU, completely disconnected it from the ML framework, and translated into exact rational numbers.
And a rational number is just a fraction. It's an integer divided by another integer, which means it can be represented with infinite precision offline. But rounding the float-32 outputs into exact fractions introduces a new problem, right? If you round the numbers, how do you ensure you haven't accidentally broken the delicate constraints of the tree?
Every single derived quantity had to be evaluated offline, using exact rational arithmetic. First, they proved that the maximum entropy certificates, which rely on a complex lemma to bound the error using Lagrange multipliers, remain mathematically valid under the rational rounding.
Meaning the rounding didn't violate the entropy conditions.
Exactly. The ultimate test, though, is the final inequality constraint of the entire laser method. The theorem basically states that the total retained exponent plus the total matrix size multiplied by omega must be greater than or equal to $2 1 log 12 over c plus 2, where Joule's 5s.
Okay, wait. We have a logarithm in the formula. Logarithms of integers usually yield irrational numbers.
Right.
And an irrational number goes on forever without repeating. You cannot execute an exact rational proof if you have an irrational log just sitting in the middle of your inequality.
This is where they used safe rational bounding. They systematically replaced every single logarithm in the evaluation with a rationally rounded fraction. The key is that they rounded in the conservative safe direction.
Let's make that concrete for the listener. Imagine the irrational logarithm evaluates to, say, 2.807 followed by an infinite string of decimals.
Okay.
The formula demands that your optimization output must be greater than that logarithm. If you replace the logarithm with the exact fraction representing 2.81, you have made the target slightly harder to hit. So if you can prove mathematically that your output is greater than 2.81, then it is absolutely undeniably greater than 2.807.
Yeah, exactly. By evaluating all the constraints against these safely bounded exact rational fractions, they eliminated float-32 errors entirely. The ML optimization engine did the heavy lifting of finding the general coordinates within that chaotic 7 million parameter space. But the rational certification pipeline drove the flag into the ground, proving the constraints were satisfied flawlessly.
Man, let's step back and just survey the magnitude of what this paper accomplished. The DeepMind team took a notoriously stubborn, doubly exponential discrete math problem that had completely stalled out traditional solvers.
Yeah, they hit a wall.
And they converted it into a smooth, differentiable landscape using logits, softmax, and optimal transport via the Sinkhorn Op algorithm. They bypassed GPU memory limits using implicit differentiation. They brute forced a non-uniform tree onto parallel hardware by inventing phantom nodes.
The engineering alone is staggering.
It is. And then they supercharged the search space using an AI agent called AlphaEvolve. And finally, they locked the whole thing down into a bulletproof mathematical theorem using exact exact rational arithmetic. I mean, the magnitude of this drop in omega is on par with the biggest single leaps made over the entire 40-year history of the field.
It firmly establishes that machine learning infrastructure is no longer just a tool for pattern recognition or generative media, right? It is becoming a foundational engine for accelerating core scientific and mathematical discovery.
Yeah.
We are taking the hardest theoretical problems humanity has to offer and solving them with the exact same gradient descent tools used to train image classifiers.
Which leaves you, the listener, with a rather profound question to consider as we wrap up today. The authors explicitly note at the end of their paper that while we might squeeze out a few more modest improvements to omega using these ML tools, achieving the massive drops required to bring matrix multiplication down to true aura will likely require entirely new mathematical ideas.
Right. The current framework can only go so far.
Exactly. Right now, we are using AI and gradient descent to perfectly optimize existing mathematical frameworks, like the 40-year-old laser method. We are finding the best possible parameters within a human-designed landscape. But how long until we can use systems like AlphaEvolve not just to tweak the code of our current ideas, but to discover the entirely new mathematical paradigms we hadn't even thought of yet?
Yeah, that's the real frontier.
When does the AI stop being the hyperparameter optimizer and start being the mathematician?
Well, we have proven we can navigate the impossible landscapes of 7 million parameters to perfect our current theories. The next era of complexity theory will be letting the machine build a new landscape altogether.
I couldn't agree more. Thank you for diving into the slop with us. We will catch you on the next one.